Okay, and then taking in-class attendance as usual. Okay, so most likely this is the last lecture, right? Next
Probably.
week, yeah, next week we are going to study on Tuesday, and Thursday you take the exam, and then Monday you're going to present, and that's it. Okay? Oh, actually, don't forget the homework.
Oh, is it the following one?
Oh, that's right. We have some kind of homework. Let's just take a look.
Yes, the following Monday is our last day. Okay.
I don't know. I don't even remember. So, okay, let's just double check things you need to be done. Oh yeah, due to multiple requests, 2 people requested from same team. I'm not so first person said, "Well, you have to postpone." I said, "Well, need a multiple request," and then the other person said,
Wow.
"Okay, that's multiple request. That's fine."
Wow.
So anyways-
You should have said due to multiple team requests. So you should have said.
Well, I can change it based on Jimmy's.
No, it's okay.
Well, whoever requested
No.
this is gonna kill you, but. So anyways, I postpone it, but it's not gonna be Tuesday, but Monday. Not gonna be 11 a.m., but 8 a.m. So I basically give you a weekend to finish up. I think seriously speaking, if you keep pushing back this phase 3, your phase 4 is gonna be like a terrible quality, and then everybody laugh at it, mock at you kind of thing. So let's just avoid it. So let's just get it done as quick as possible, then start finishing up phase 4. Phase 4 requires, based off of the performance, you're going to finalize your design with the stability analysis, okay? That's phase 4. So phase 4 needs phase 3 configuration, because phase 3 configuration is pretty much your final configuration. Then based on that configuration, you're going to do performance analysis, okay? Unless you complete phase 3, you can never do phase 4. You need to have static margin, you need to have a neutral point, you need to have center of gravity determined. Okay, then otherwise you can never do stability analysis. So do not try to push back. Okay, let's get it done as quick as possible. So this is the pretty much the final deadline for phase 3. So let's just get it done by Monday, 8 a.m. Okay. Any question? Any question, especially any question, whoever it is requested this postpone. I mean, I'm not going to name who did it, but I hope you're okay. Please respond, react, or whatever, express yourself. Are you listening? Are you listening? Hello, hello.
Yes.
Please react. Okay, please react. Like a thumbs up, something like. Okay, the only person I see is Jordan. All others are probably sleeping, logged in, sleeping.
Oh,
Hello. Oh, okay. Okay. Connor, are you there?
you did.
Connor? That's okay. It's okay. Let's just move on. Assuming, well, because his teammate responded, so assuming he's okay. Okay, so, and also, what about homework of Unit D1? This is Tuesday, next week, okay? So you have to get phase 3 done by Monday. Then Tuesday, you have to get this homework, Unit D1. This is last homework assignment. Get it done by Tuesday, 11 a.m. Exam is on Thursday. That means next week, Tuesday, I'm planning not to do any lecture. I'm trying to finish up D1, D2 today. Whatever the leftover of D2, it's going to be all up to you, because D2 is master note, okay? Unit D2 is just master note. Everything is included.
Wait, are we getting tested on D2?
Hey?
We're getting tested on D2?
No.
Oh, okay.
Unit D2 is not going to be on exam. There's no example problem. Actually, Unit D2 is important for your P4, phase 4, okay? It's not going to be on exam, no. All right. Good question, actually. So I have no desire to test you on Unit D2. Unit D1 might be included, because we did the example problem in class, okay? Phase 4 is Monday. Do you have any question about this final schedule? Any question? Okay, so this is it, all right? So let's just finish up Unit D1 today, and let's just getting into Unit D2. So Unit D1, page 12. There are a few more important things I have to cover in Unit D1. One of them is, do you remember the example program here we did in last class? And we somehow used the code, okay? This is a main wing code is usually used to normalize the distance, such as location, center of gravity, location of aerodynamic center. Oftentimes, we are going to use C over bar. This is a mean code. What is the meaning of this mean code? Representative code. Is it average value if it's tapered? Yeah. But suppose if it's not the tapered wing, some weird shape, how do you determine this code which is representative of the main wing? This is called mean aerodynamic code, MAC. Okay. So next page, I'm going to talk a little bit about what is the mean aerodynamic code, which is this. So suppose if you come up with a main wing design, somehow you have to determine the representative code ranks, because this code ranks is going to be used to normalize your distance, okay? So in other words, where is the center of gravity location? It is, location percent measured from the nose or measured from leading edge of this wing, okay? So this is mean aerodynamic code, C over, but typically this is going to come up with an equation. This is the equation to determine mean aerodynamic code, okay? If the wing is untapered, of course, mean aerodynamic code is called. This means this is a chocolate bar wing. If you design chocolate bar wing, mean aerodynamic code is called, of course, yeah. And also at the same time, what is the location of mean aerodynamic code measured from the root, which is this? Measured from the wing root, where is the location of mean aerodynamic code? This is YMAC. You need to determine that too. Here we go. So this is for untapered or linearly tapered wings. You can determine span-wise location of MAC. So it is actually quite important here. By knowing mean aerodynamic center, you can actually determine the aerodynamic center of the wing. MAC corresponds to aerodynamic center of the main wing. You remember, aerodynamic center is about quarter code for a cross-section of a wing called airfoil. Now, wing's aerodynamic center is located also approximately at the quarter code of the MAC. So wing's aerodynamic center is right here, quarter code of MAC. So this is the location, okay, span-wise location and code-wise location of main wing's aerodynamic center. In order to determine such a thing, location of MAC, which is why MAC is called also quite important. So you need that kind of information. Okay, it's quite important here. So this is the aerodynamic center location of the swept wing. Of course, this is based on the leading edge sweep angle. So if the sweep angle is 0, of course, 0.25 MAC, obviously. Okay. So anyways, so those are the quite important information to determine your main wing's aerodynamic center, location-wise on the span, and also usually location of the MAC's quarter code is your main wing's aerodynamic center. Okay. Next page. Suppose if you consider two things, strake and fuselage, those things to come into play for whole airplane configuration. Okay. Suppose if your aircraft is equipped with strake, such as F-16, F-17, leading edge extension, LEX, that's F-16, yes, right. Leading edge extension, this is F-18, and then strakes is F-16. It's kind of slightly different wording, but it is additional wing surface, usually stretched on the leading edge, connecting to the fuselage, okay? If such a thing is equipped, it is going to have an impact, okay, on the location of neutral point. So this is the equation. And also fuselage also have some contribution of creating lift. So it is going to alter a little bit about the neutral point. So this is the location of neutral point. So you have to come up with those two information of leading edge strakes and also fuselage. Okay. Important thing, moving the aerodynamic center forward is destabilizing. That means you don't want to shift your aerodynamic center moving forward, which is essentially similar to shifting the center of gravity aft. It's the same thing. In other words, it's not really contributing to the positive stability, right? Okay. So if your airplane comes with big fuselage and huge strakes, if you add such a thing, sometimes it is going to affect on the size of the horizontal tail. In other words, you may end up having a necessity to increase your horizontal tail sizing because those big fuselage and leading edge extension, although it is desired, it may cause some negative contribution to the static stability. Okay. So this is something quite interesting. At the stage that you're going to finalize your configuration, you're going to actually run the stability analysis using software that actually reveals those kind of things. And once you realize, hey, our stability surface is too small, you have to make it bigger and then run the simulation again. That is one of the advantages of the using software. Okay. This is also hand calculation method of the location of neutral point. Okay. Now, neutral point can be computed using X55, so you can rely heavily on that, or you can do a hand calculation by using the definition of the location of neutral point. Neutral point, by definition, this is the location Cm alpha becomes 0. Okay. So you're going to set the Cm alpha equation from the previous page and set equal to 0 to determine xcg as a location of Cm alpha equal to 0. This is called location of neutral point. NP location. Okay. X over bar means this is a normalized value. So this is percent measured from typically leading edge of a main wing, of course, normalized by MAC, mean aerodynamic code. Okay. And then static margin is basically difference between the neutral point location to the center of gravity location normalized. This is the static margin. We talked about that. Okay. So let's just take a look at the one more example, which is very, very simple example. Let's just finalize unit D1. Example D13. A design concept for a jet cross air support aircraft. This is a schematic picture. Uses a configuration just as shown in this figure. Both the wing and the horizontal tail of this aircraft have rectangular platforms. The aircraft tail volume ratio is given. This is xcg minus xac. This is static margin, isn't it? This is what? No, it's not. xcg minus xac normalized. That means this distance, yeah? Okay. xcg minus xac is this distance is 0.01, which is right here. Okay. Okay. The aircraft is flying at an angle of attack such that its main wing generates CL equal to 1.0. CMAC for the cambered wing, this thing, is negative 0.0025. It looks like MAC is in the figure is pitching up moment because this is a positive direction. So negative sign means you actually nose down moment around aerodynamic center, which is kind of common if you have a camber. What must the horizontal tail lift coefficient be? In other words, you want CLT, right? What is the CLT you need for horizontal tail lift coefficient in order to trim the aircraft? Okay, once again, this is a simple problem about statics. Summation of the moment around center of gravity set equal to 0. That's the trim condition. So in order to trim this airplane, you take the summation of all the moment, Cm location Cg must be equal to 0. So that is Cm of aerodynamic center plus, okay, Cl times x over Cg minus x over AC minus Cl times tail volume ratio. Now, important thing here is everything is coefficient. Okay? Normalized. Okay. So from here, simply you can just plug in to determine CL tail. So CL, what's CL? This is CL tail, sorry. So this is CL tail times volume tail, volume ratio of the tail. So from here, the equation will become CMAC plus lift coefficient main wing times x over CG minus x over AC. By the way, this is essentially static margin, isn't it? So this is minus 0.0025 plus CO is 1.0 for main wing times static margin 0.01 divided by 1.0 volume tail ratio. If you compute it, you need to have 0.0075. It's tiny value because this is a trimming requirement. So you need this much lift coefficient produced by horizontal tail in order to trim this airplane. Okay. Of course, you need a lot more requirements, of course, added onto your wrist maneuvering requirements. Suppose if this is stabilizing at the same time, maneuvering or controlling surface, how big it should have, and then how much angle of attack of trim, alpha trim, you're going to dedicate for trimming. And the rest of the angle of attack need to be set aside for controlling. So those are the requirements you have to consider toward the end, phase 4. Okay. Next page is dynamic longitudinal stability. I have a video, so let's just rely on someone else's explanation here. Okay, so I have a video. First of all, let's just take a look at understanding airplanes' longitudinal and directional stability.
Hello, this is Tim. Today we will talk about aircraft stability and why stabilizers are needed. First, let's see what is the meaning of stability. Let's consider an aircraft in flight. The ability of this aircraft to withstand any disturbances and continue its normal flight is called as stability. Stability can be classified into static stability and dynamic stability. We will look at static stability in this video. What is static stability? Static stability refers to the initial response of an aircraft after it is subject to a disturbance. After the disturbance, if the aircraft has a tendency to come back to its original attitude, then it is said to have positive static stability. After the disturbance, if the aircraft has a tendency to deviate away from its original attitude, then it is said to have negative static stability. After the disturbance, if the aircraft tends to maintain its new attitude, that is not coming back or not deviating from the original attitude, then it is said to have neutral static stability. On comparing the positive static stability, negative static stability, and the neutral static stability, we understand that the aircraft should have positive static stability. This stability is entirely dependent on the aircraft design. The positive static stability can be divided into longitudinal stability, lateral stability, and directional stability. Let's look at longitudinal static stability. This refers to stability of an aircraft after it suffers a disturbance in pitch. To understand this stability, we will have to take a closer look at the wing airfoil. On the airfoil, there is a point called as center of gravity or CG and another point called as center of pressure or CP. At the center of gravity, the aircraft's weight force acts downwards and this is a fixed point. At the center of pressure, the lift force of the wing acts and this point moves based on the lift. Let's keep the CP ahead of the CG. Now, if there is a disturbance in the pitch, the tendency of the aircraft would be to deviate from the original attitude. This will result in negative longitudinal static stability. Now let's keep the CP behind the CG. If there is a disturbance in pitch, the lift and weight forces will create a tendency to return to the original attitude. This is called as positive longitudinal static stability, which is required on the aircraft. The lift and weight forces together will form a couple, which will push the nose of the aircraft downwards. To prevent the aircraft nose-down condition, the horizontal stabilizer is installed. To remove the nose-down condition, the horizontal stabilizer needs to give an aircraft nose up. This is done by creating a downward force at the tail section. This will give us positive longitudinal static stability and level flight. Next, we will look at lateral static stability. If the aircraft is subject to a disturbance in roll, then it tends to roll with the wind. For this disturbance, stability is provided by the vertical stabilizer and the wing structure. As the aircraft rolls due to the disturbance, the lift increases on the downgoing wing as the angle of attack on this wing increases. The lift decreases on the upgoing wing as the angle of attack on this wing decreases. This will create a tendency on the aircraft to roll back to its original attitude, which will give us the positive lateral static stability. During the disturbance, the vertical stabilizer provides resistance to the roll. This will improve the positive lateral static stability. Next, we will look at directional static stability. This is important when the aircraft is subject to a disturbance in yaw, causing the aircraft to turn. The vertical stabilizer becomes the primary surface to provide the directional stability. During the disturbance, the nose will yaw in the same direction as the wind. The tail will yaw in the opposite direction of the wind. This will result in an increase in drag at the vertical stabilizer. This creates a tendency to yaw back to the original attitude, which will give us the positive directional static stability. The static stability of an aircraft includes the longitudinal static stability, lateral static stability, and the directional static stability. The positive static stability is achieved by a good aircraft design, or more specifically, a good design of the wing and the horizontal and vertical stabilizers. Thank you for watching and please subscribe.
Okay. All right, so that actually sums up for static stability. And then I have actually another video talks about dynamic stability. So I'm going to skip this page and go right into unit D2. Okay, so because unit D2 talks about the other two, directional and lateral stability. Okay, so at the very end of unit D2, I'm going to show you the video about the dynamic stability for both longitudinal, lateral, and directional. So let's just move into unit D2. So unit D1, we talked about longitudinal static stability. And also, I want to talk about lateral and the directional stability in this unit D2. By the way, this unit D2 is a 100% master note. You're given everything. I'm not going to pick up any problem here for testing or anything. Okay. So first of all, directional stability is basically, that's a yawing, okay? So suppose if you yaw your airplane should have a natural tendency to go back to the original position. That is the, wait a minute. Directional, okay, sorry. So that's a directional, okay, here we go. I should say directional first. So this is a directional or yawing stability. This is the static directional, actually yawing stability. So this is the criteria. We want to talk about something called CN. CN is yawing moment coefficient. Here we go. And then CN beta. Beta is a side sweep angle similar to the pitch angle alpha. Beta is a side sweep angle. So CN beta is a yawing moment coefficient curve slope. Okay. So in order to have a static directional stability, positive stability criteria is CN beta must be positive. If you design your airplane with CN beta negative, it is basically directionally unstable. If you're disturbed, you just keep spinning. That's bad. The other way around is a lateral stability, which is a rolling. Okay, so this is kind of interesting because rolling, which way is positive? This way. So right wing down is positive rolling. Okay. So let's just take a careful look at it. Now, this is a funny L. This is also another thing I really don't like to control. But this L is a funny L because this is not the rift. No, it's not rift. Okay. So this is a rolling moment coefficient. L is a different meaning here. So that's why I'm just keep changing the type of fonts. This L is not the rift. Regular L is a rift. This is a funny L. This is a rolling moment coefficient. This is a rolling moment coefficient curve slope, CL beta. Okay. So the requirement for positive static lateral stability is that an aircraft roll away from a side slip. So negative of CL beta is required. This is completely opposite in terms of sense of a sign. Okay. CN beta must be positive, but the CL beta must be negative. I always get confused after I saying it by myself. Okay. Is this consistent with some other professors talking about that? Really? Okay, funny. So this is a Air Force Academy standard, so everybody need to basically follow through. So positive rolling condition is if the side wind hits your wing, you have to roll away from it. Okay, so that's what it is. So this is the criteria of positive lateral stability, static stability. And then I'm going to take a look at the few impacts. Suppose if you have a wing sweep and if you have a different wing aspect ratio, what happens to the stability contribution? Okay. So first of all, when the aircraft is yawed, it is going to have a positive side slip angle. Okay. Now, if you have a wing sweep, okay, right wing is less swept relative to its velocity vector than its left wing. So the aircraft will roll left, that is positive contribution. So if you have higher wing sweep, in terms of lateral motion wise, you have a better static stability, actually. Interesting. And then also higher aspect ratio airplane has a tendency to be better in static stability in rolling. Okay. Okay, here we go. So next page. How about the placement of the wing? High wing, this is a mid wing, this is a low wing. Now, this figure is also kind of confusing. You have to be very extra careful about, okay? So those three figures, as you see, this is the placement of the wing itself. This is a front view, okay? So you are looking at airplane from front, okay? This is front view. So cross flow comes in and hit this wing. So this wing increased the lift, this more than this wing. This wing is upwind wing. This is the downwind wing. Since cross flow is going to give you a tendency to roll away from the cross flow, high wing actually has a tendency to stabilize for lateral motions. And that means it's better stable for rolling. Mid wing has no impact, but suppose if you go for low wing actually has a negative impact on rolling stability. Okay. Next is, okay, what about dihedral? Another kind of confusing aspect here is those three figures are all rear view. Okay. This is a rear view. Be careful. It actually says so here, but rear view. So you're looking at airplane from the tail. Okay. This is rear view. This is the front view. This is rear view. So suppose if you have a positive dihedral, the cross flow comes in, upwind side of the wing increase the lift more than downside wing, downside wind, downwind side wing, downwind side wing. Okay, anyways. So how about that? Dihedral, positive dihedral actually stabilizes, okay, lateral motion. But the negative dihedral is completely opposite. It has a tendency to destabilize the rolling motion. Okay, that's what it is. So that was what? What's the airplane with this kind of wing? I don't know. Harrier has this kind of wing. Okay. How about the very high, tall vertical tail? This is actually positively contribute to the rolling, static rolling motion. Okay. And also another good aspect here is suppose if you have a T-tail, let's say, if you have a horizontal tail placement just as on top of the vertical tail, this is a T-tail. This is going to have a blockage effect of the cross flow. It actually increases the tendency of stabilizing effect. That is the tall vertical tail. Okay. So suppose if you have a vertical tail with T shape, this is end plate. What is the airplane with such a thing? I was thinking about, okay, what is the airplane that actually taking advantage of such a thing? This is the airplane. Okay, so this is the C-17 Globemaster 3. So this is a T-tail. It's actually, relatively speaking, huge vertical tail plus T. So they have a hard time having a static stability of lateral motion. So this is a T-tail. That's a huge vertical wing also. Okay, of course, this is a cargo airplane. So you need to stabilize just about any configuration of center of gravity shift. It's a tough design. Okay. Okay, so next is a dynamic lateral and a directional stability. There are so many different modes: spiral modes, Dutch roll, roll mode, adverse yaw, and spin. Again, I'm going to show you a video to discuss about those things. Bottom right, X55 actually can cover all of those dynamic stability modes. You can simulate all of those. So you can discover as a team goes toward the phase 4, you can just pick up the software trying to simulate all of those different dynamic stability modes, trying to see if your airplane is stable dynamically speaking, all directions, longitudinal, lateral, and directional. Okay? And just to show you, page 7 to 10, those are just a 100% example or exercise for your phase 4 project. So I'm not going to go over it, but this actually sets you an example for phase 4 analysis. You're going to do phase 4 using software, X55. And then this is actually example. If you want to do static stability analysis by hand, this is the process. Lots of equations. You're probably not going to do it because your software actually can take care of all of those things. This actually includes the supersonic flight, static stability, and then static margin computations. F-16 is, of course, supersonic capable airplane. So you have a hand calculation equations available. if you go for supersonic, basically the aerodynamic center shifts to the 50% code, not the quarter code. That's a big change, but those are the equations. Okay, so this is just the exercise or comparison. If you want to go for like a hand calculation and then compare against, which is not required for phase 4, if your team is willing to do that, this is something you can look at. Okay. Again, this is above and beyond subject, so I don't cover it. This is just the FYI information. If you want to do stability analysis all by hand, I think you guys did it, taking S&C class. Didn't you do this?
The spreadsheet thing.
This hand calculation thing? Really? Really?
Just gives us one.
You did, right? You did, right? Who's the teacher? Eh? Boardington.
Yeah.
Professor Boardington let you do it. Who's your teacher? I mean, you didn't. Oh, okay. I didn't hear anything. I'm sorry.
Oh my goodness.
Hand calculation. There we go. Oh, that's a great professor. He let you do hand calculation. This hell. This is like, oh my goodness, kind of hand calculation, right? Look at that.
No.
No, right? Okay. Yeah, sure. Since I'm not S&C person, I'm not gonna let you do it anyways. But this is just this is just FYI information. If this is S&C class, of course, this is part of the requirement. But this is flight mechanics performance. This is not stability and control class. Okay. So this is just for your information. If you want to do hand calculation for static stability, this is it. Okay. It's a good to have kind of information. So let's just take a look at the video to conclude this semester. Okay, so this is the video part 2, dynamic stability analysis. Here we go. Okay. Okay. I hope I have audio.
Hello, this is Tim. Today we will talk about the dynamic stability of an aircraft. First, let's see what is stability. Stability refers to the response of an aircraft after it is subject to a disturbance. Stability can be classified as static stability and dynamic stability. I have already discussed about static stability in my previous video, Understanding Aircraft Stability. So, in this video, I'll be discussing about dynamic stability. First, let's look at what is dynamic stability. After a disturbance on an aircraft, the aircraft's attitude changes. The initial response of the aircraft is called as static stability. The response of an aircraft over a certain time period is called as dynamic stability. Let's see what this means in more detail. This line represents the original position of the aircraft. If there is a disturbance, the aircraft suffers a deviation due to the disturbance. If the aircraft comes back to its original position after a certain time period, then it is said to have positive dynamic stability. The flight path of this stability will look like this, with the amplitude of oscillations reducing. In case after the disturbance, if the aircraft keeps deviating from its original position after a certain time period, then it is said to have negative dynamic stability. The flight path of this stability will look like this, with the amplitude of the oscillations increasing. After the disturbance, if the aircraft maintains the same oscillation after a certain time period, then it is said to have neutral dynamic stability. The flight path of this stability will look like this, with the amplitude of the oscillations being constant. So the dynamic stability of an aircraft can be divided into positive dynamic stability, negative dynamic stability, and neutral dynamic stability. The aircraft should have positive dynamic stability. Now, let's look at a few cases starting with longitudinal dynamic stability. This stability is applicable if the aircraft is subject to a disturbance in pitch. The oscillation should be quickly damped and the aircraft should return to its original attitude. But if the oscillations are not quickly damped, then it is called as fugard oscillation. In this, as the aircraft's altitude increases, the speed decreases, and as the altitude decreases, the speed increases. So, the potential energy, that is the altitude, and the kinetic energy, that is the velocity, are interchanging. So this can be called as a constant energy oscillation. Now let's look at a few cases related to lateral and directional dynamic stability. We have to combine these two because the roll and yaw are interconnected. This means that if the aircraft yaws towards the right, the left wing will move faster than the right wing. So more lift is created on this wing, hence the aircraft will automatically roll towards the right. In a similar case, if the aircraft rolls towards the left, the lift vector gets tilted towards the left. So the aircraft will automatically yaw towards the left. One of the cases related to lateral and directional dynamic stability is spiral instability. This occurs if the aircraft has positive directional stability but not enough lateral stability. The flight path after a lateral disturbance will look like this. In this instability, the bank angle increases, the altitude decreases, and the turn becomes tighter. Another case related to lateral and directional dynamic stability is the Dutch roll. This occurs if the aircraft has positive lateral stability but not enough directional stability. The Dutch roll is a combination of roll and yaw. After the disturbance, the aircraft will try to come back to its original position, but since the directional stability is not sufficient, it will oscillate about its original flight path. In order to avoid cases like phugoid oscillation, spiral instability, and Dutch roll, the aircraft should have positive dynamic stability. So let's look at how to improve the positive dynamic stability. First, the aircraft should have positive static stability. For static stability, the center of pressure, Cp, should be behind the center of gravity, Cg. The wing design can be modified into a swept back wing and giving a small dihedral or anhedral angle. A proper tail section design, which means a good design of the horizontal and the vertical stabilizers. After the disturbance, positive inputs by the pilot or the autopilot to dampen the oscillations with the help of control surfaces such as elevators, rudder, and ailerons will improve the positive dynamic stability. Thank you for watching and please subscribe.
Okay, so that actually sums up the dynamic stability of all three directions, longitudinal, directional, and lateral. Okay, so again, this is like open-ended for phase 4. Dynamic stability is not even part of this class curriculum. Okay, so just do your best. That's what I say, and then have lots of fun discovering what the software can do. That's the important thing. Okay, so this really concludes this semester's lecture of this class AE317. Do you have any question? If not, this is the list of things you need to do. And then next week, Tuesday, we have no lecture. It's a study day. Thursday, don't forget, we have exam right here in this classroom at 12 noon. Right after your lunch, you take the exam and happily walk out of the classroom next Thursday. And then final presentation, you guys know that. It's Monday, May 3rd, 10:15 to 12:15. Once again, in here, this classroom, you're going to present based on your PowerPoint. Okay. So that's it. Any question? Have a great day.
What about extra credit for the?
Oh, I'm going to announce it. Don't worry about next week, before the end of the semester date. What's your request, by the way? What do you desire? Oh, if you say I don't know, I'm not going to probably do anything. By the way, do you need anything to bump up your grade? I don't think so. I mean, this class. I mean, you are pretty happy about where you stand, right? Okay, so I'll do something. Don't worry about it. Just to finish up your semester good. Okay, I'll give you a small incentive for doing end of the semester course evaluation. I'm going to announce it probably Monday next week. Okay. Any other question? Have a good day. Okay. Have a great weekend. See you guys back next Thursday for exam. Just keep contacting me with Microsoft Teams. Okay, if you have any question. All right. Have a great weekend.
Can you give the equations on these are any different to us? Or do we